Okay. All right then. So welcome everyone, and welcome Ali. Ali is almost a regular speaker at our seminars, and this time it's in the evening edition of MOPA. So we have people from a completely different side of the globe. So welcome everyone, and Ali will talk about arithmetic with a class of indiscernibles.
Thank you very much, Roman. It's a pleasure to be seeing all my colleagues across the world one more time through this medium. So I will be talking about some recent work that I did, which connects indiscernibles both with set theory and also arithmetic. So let me see if I could go to the next slide. There we go. I've put here the coordinates for where the manuscript is right now with Math Archives. It's under review, and I'm just making some small changes. So probably by next week, I'll be putting a new version, but it's going to be just catching typos, that kind of thing. In this manuscript, the majority of the paper is about a system of set theory with a class of indiscernibles, a proper class of indiscernibles, denoted ZFI with a less than symbol. Basically, you have to throw in a global well ordering in the universe to make things work properly. In this talk, I will be focusing on the arithmetical side of the story. So basically about 3/4 of my slides are devoted to Peano arithmetic with indiscernibles, and only in the last quarter of my time, I will come back to set theory as a way of comparing and contrasting the behavior of these two theories. I already told you what ZFI does. It's basically a system of set theory with a proper class of indiscernibles. The system I'll be talking about today is PAI, I for indiscernibles. It's Peano arithmetic equipped with an unbounded class of indiscernibles over the ambient arithmetical structure. Okay, so I already told you that I'll be focusing on the arithmetical side of the story, so I could move on from this slide to the next. Let's look at the axioms of PAI. So it's a theory formulated in an extension of the language of Peano arithmetic, where you throw in an extra unary predicate for the indiscernibles, that's capital I. The axioms of the theory come in the following three groups. So I'm using L of PA parentheses I as a shorthand for this extended language. And I'll be using the epsilon symbol x epsilon I instead of just writing I of x. Okay, so here we go. The first group of axioms is basically the natural extension of Peano arithmetic in this extended language. So in the trade of models of arithmetic theorists, this is PA star. So induction, in the induction scheme, we're allowed to use formulas mentioning I. Intuitively speaking, I can be used in arithmetical reasoning. It has oomph to it, so to speak. Also, the sentence which says I is unbounded in the universe, hence sometimes me saying this is a proper class. And you also want to say that these the members of I are order indiscernibles. So that's through a scheme. So for each formula phi in the arithmetical language, you have a sentence which says that I is phi indiscernible, that I haven't shown you yet, but it's pretty much what you would write down if I told you to write down some such axiom. Remember, phi is an n-ary formula. So for every x1 through xn and y1 through yn, all coming from I, if x's are increasing and y's are increasing, then phi of x1 through xn holds, if and only phi of y1 through yn holds. So this is precisely the idea of being order indiscernibles. So we have basically one axiomatized essentially by a scheme, two a sentence, and then three another scheme for the axioms of PAI. So here are some rather elementary considerations looking at the axioms and saying something about them. If you give me a model M, comma I, where M is a model of PA, then this formation M, comma I is a model of PAI. If, first of all, PA star holds in this expanded structure, I is unbounded in M, and I is a class of order indiscernibles over M. So right off the bat, we note that the standard model of Peano arithmetic has no expansion to a model of PAI. This is basically because the standard model is pointwise definable. So you could easily distinguish the elements from each other. So it cannot have indiscernibles. On the other hand, we have a lemma, which I'm calling finite interpretability lemma, which says that if you give me any model of PA and any finite set of axioms of PAI, I'm calling that finite set capital F, then you could actually get hold of a parameter-free definable subset I of M, such that when you append I to M, you satisfy that fragment F of PAI, the finite fragment that was specified ahead of time. So each finite fragment of PAI is interpretable in every model of Peano arithmetic. So let's look at just the outline of the proof. In blue, you see the expression every finite subtheory of PAI has an omega interpretation in PA. So here, an omega interpretation is an interpretation which doesn't change the meaning of numbers. So you're simply defining what I is supposed to be, as opposed to also redefining what the numbers are supposed to be. In an interpretation, you're allowed to also redefine what the universe of the model you're interpreting is allowed to be. Here, the universe doesn't change. Okay, it's basically the formalized infinite Ramsey theorem at work. PA has the capacity that, given any list of arithmetical formulae, suppose you have k of them, phi1, which has n1 variables, all the way to phi k, which has nk variables. Given any such list, you could find a single arithmetical formula such that provably in PA, H is unbounded. That's property number one. And H is indiscernible as far as phi1 through phi k are concerned.
Sorry,
Yes,
so PA star was, because you have PAI is your theory of indiscernibles. So
yes,
I'm looking at the first point.
Yeah, so,
but
yeah,
what is PA star?
Yeah, sorry, PA star, I said something about that quickly in the previous slide, but I'll be glad to repeat it. PA star basically is PA in the extended language. So the axioms of PA star are exactly the axiom of PA, plus you allow formulas mentioning I to be used in the scheme of induction.
Yeah. Okay. So yeah, so just you can use I as some kind of predicate.
Exactly. I guess set theorists call that sometimes I is amenable or some such thing.
Okay. Yeah. That's fine.
Any other questions so far? Okay. So this easy lemma, easy because it's quite well known that PA is capable of handling the infinite Ramsey theorem in a schematic way, has some important consequences. It tells you that PAI as a theory is a conservative extension of PA in the sense that if PAI proves a purely arithmetical sentence, already PA proves that. Also, if you look at the proof that I just gave you, it's pretty uniform. I didn't care about what the model was. Given phi1 through phi k, you could come up with H uniformly, independent of what model you're looking at. That gives you an interpretation of PAI in PA. And that shows that, so this theory is mutually interpretable with PA, but they're not bi-interpretable. Now, to see that they're not bi-interpretable, just recall the fact that the standard model of arithmetic cannot be expanded to PAI. so that's the quickest proof that they cannot be bi-interpretable, because if they were bi-interpretable, then you would be able to define indiscernibles for the standard model of arithmetic. PAI is interpretable in ACA 0, but not vice versa. So remember, ACA 0 is the analog of Gödel-Bernays set theory for ZF. It's a finitely axiomatized fragment of second-order arithmetic that is conservative over Peano arithmetic. It's known that ACA 0 obviously interprets PA, and since PA interprets PAI, so PAI interprets ACA 0. That's the first part of this corollary. The not vice versa has to do with the fact that if PAI was able to interpret ACA 0, then PA would. And it's well known that PA does not interpret ACA 0. So at the level of, if you're ordering by mutual interpretability, PAI and PA are in the same clump, but ACA 0 is above them. It interprets them, but not vice versa. Okay, so this is the end of just basically getting consequences from the finite interpretability lemma. Now this slide talks about the notion of satisfaction class and basic satisfaction classes and truth classes. They happen to be actually playing an important role in a better understanding of PAI. So I'd like to begin with just fixing a sentence, sat of s comma x. It's a formula in the language of Peano arithmetic, in the extended by an extra binary predicate s for a satisfaction predicate. So this formula expresses that S satisfies Tarski's compositional clauses for all formulas of length at most x. So S is well behaved vis-a-vis Tarski's clauses for formulas up to x. So it's well known that you could write such a sentence. We're going to fix that. And then I'm going to be looking at a theory that is often known by people who are who study truth theories as UTB. The U stands for uniform, and T and B stand for truth by conditionals. So this theory is similar to PAI. It's also formulated in an extended language, except that this time you add a unary predicate, not denoting indiscernibles, but basically a truth predicate that is supposed to be well-behaved, and the well-behavedness in this context is more modest than just asking for compositional clauses. You basically want sentences of this blue form that I've written here for all x, phi of x holds if and only if t holds of this sentence, of course, of the Gödel number of that sentence. That x dot is the Pfefferman x dot notation, so it's the numeral representing x. So that's the meaning of this phi of x dot. So you notice that you have the axioms of PA star, again, the same PA star that I was just reminding Andres about. So we have T, you can participate in the induction axiom, and then you have these uniform truth by conditionals. Okay, so the third bullet item is just a definition, just like the first bullet item. It reminds everyone what we mean by a partial inductive satisfaction class. This is, of course, one of the most important concepts in models of arithmetic these days, but I'm putting it here because I wanted to, first make sure that everybody is following exactly what I'm talking about, but also show its connection to UTB in a quite clear way. So a partial inductive satisfaction class is a subset S that you could append to the model M, such that, again, PA star holds. The same PA star now, of course, means you can use S in the induction axiom. And for some non-standard C in the model, S is well behaved for all formulas of length up to C. So S satisfies Tarski's composition clauses for formulas up to some non-standard length. Of course, it might be better than that. It might also satisfy them for formulas of longer length. But as far as we're concerned, we care about S being well behaved on all standard formulae. That's what this quantifier for all I less than C will do. And also it's important that we have PA star, because if we drop that and we drop this less than C and insist that for all I set of Si, then we get the notion of a full satisfaction class, which is also important. But we won't be needing full satisfaction classes for this discussion. Okay, so here's a folklore proposition which connects UTB to partial inductive satisfaction classes. A non-standard model of PA carries a partial inductive satisfaction class if and only if it expands to UTB. It's a straightforward argument. And the folklore theorem is that if you take any model of PA of any cardinality, if M is expandable to UTB, I should have written here, and also M is non-standard. So if M is non-standard and expandable to UTB, then M is recursively saturated. Notice that if M is the standard model, then it is expandable to UTB because the usual Tarski truth predicate satisfies, of course, the uniform by conditionals. So in this folklore theorem in part 1, I should have inserted if M is non-standard and a model of PA of any cardinality, then it's recursively saturated. Part 2 is the converse of part 1 for if M is recursively saturated and countable, then M has an expansion to UTB. This second part uses the resplendence property of countable recursively saturated models, and it's known that part 2 is false without the countability assumption. Okay, with these in mind, I can now tell you what's the main arithmetical result that I'll be talking about. An analog of this result is also true for set theory, and it plays an important role actually in part of the results that I'll be later talking about. So, so it turns out PAI is basically, expanding to PAI is just another way of saying that M carries a partial inductive satisfaction class. And this is a model M of any cardinality now. Give me any model of PA of any cardinality, then M has an expansion to PAI, if and only if it carries a partial inductive satisfaction class. So one direction of this is pretty straightforward. I'm going to go through that first. The right to left direction. So you have given me the assumption that M has an expansion to an inductive satisfaction class, and I need to show you how it expands to PAI. So given the S with the indicated properties, we write a formula in the extended language with one free variable. And the formula, let me go through it slowly. So basically, the formula says there is a definable, in the sense of S, unbounded homogeneous set for all arithmetical formulas of length at most x. So because we have S available, then to be definable means there is basically a formula, so a syntactic object, such that when S evaluates that syntactic object, because S is after all a satisfaction class, then the subset of the model that you get is well behaved when it comes to formulas of length at most x. So this is just a formula right now, but since we saw the schematic provability of Ramsey's theorem in PA, for each natural number n, M comma S satisfies phi of n. And therefore by overspill, M comma S satisfies phi of C for some non-standard C. Notice we can use overspill because we chose S to be inductive in the sense that PA star holds. So in case you're wondering, where is PA star going to play a role? It just did right now by the overspill principle that I just used. Now, this tells us that there is an unbounded definable, parametrically definable set I, parametrically definable in M comma S, that is basically indiscernible for all standard formulas, because it's indiscernible for all formulas of up to C, let alone all the standard ones. So this is the end of one direction of the proof. Let me pause for a second in case there are any questions or ambiguities.
Well, no ambiguity, Ali, but the overspill that you're doing is for one particular sentence, and it's not of a high complexity. So P star seems to be a little bit.
Oh, absolutely, absolutely. Yeah. Let's see. So in this particular case, I think, yeah. Well, we need obviously some level of
right. But
language. Yeah.
Is it easy to calibrate what?
Yeah, I think in this case we just need what's known as I think just delta zero would be sufficient because let's see.
I think so because it's all kind of.
Yeah.
Right.
Yeah, delta zero induction in the XN language should be enough.
All right.
Yeah. So I guess, so that's the same thing as being piecewise coded. So a piecewise coded satisfaction class. I haven't looked at fragments of PAI, and this is something that one can do, but yeah, it would be interesting maybe to also have a level by level version of this.
Right, because probably nothing much of interest is happening here, because then your theorem would just say that this is again equivalent to existence of some delta zero inductive partial.
Yes, exactly, yeah. Did I hear another question or another voice?
Oh yeah, sorry. Ali, I had a question. I think earlier, did you say that the standard model has no expansion to a model of PAI? So
that's right.
So then the standard model doesn't carry a partial inductive satisfaction class?
It certainly does. So this should be non-standard again. Yes, so you caught me.
Yeah. Oh, okay.
Yes, I had failed to put non-standard. Let's see. Right, so.
Wasn't your partial inductive satisfaction class, didn't that have to go up to some non-standard element?
Oh, yes.
Oh,
so I
okay.
guess that, yes. So
okay, so the definition,
thank
you
you, Bob.
define it for a standard model.
Yeah.
Okay.
Yeah, the sound of it doesn't sound like partial inductive insist on non-standardness, but it was built into it. So we're safe. Okay.
Thank you. Okay.
Any other questions or comments? Okay. For the other direction, let's see, what are the tools that we need for the other direction? So it turns out PAI is able to prove two important schemes that I'm dubbing the apartness scheme, and then later you'll see another scheme called the diagonal indiscernibility. So to state the apartness scheme, let's see. If you give me a formula with n+1 variables, so x bar is x1 through xn, and so we have phi of x bar comma y, then a parts of phi is basically this sentence you're seeing in this formal sentence, which says if I and j are both members of capital I with I less than j, and you give me any parameters x1 through xn below I, the smaller of the two members of capital I, then any existential sentence with parameter x is already witnessed before j. Let me give you another way of looking at that. So first of all, the apartness lemma says that PAI proves this. So in a model of PAI, if I and j are both in I and f of x is an arithmetically definable function, and you apply to inputs less than a, then you're guaranteed to land before j. So this ends up being pretty easy to prove using the collection scheme and the indiscernibility property and the I being cofinal in the model. So it's not a deep scheme, but it's a very useful one. That's the first important tool. The other one comes in handy also in the long run, both in arithmetic and set theory. I'm about to now explain what's the other scheme that PAI is able to prove. So this one looks much more complicated, but then I'm going to draw a picture for it and hopefully make it pretty clear what it is saying. It just in formal symbols, it looks pretty complicated. So if you give me a formula in arithmetic which has variables, this n plus 1 plus r, the n part refers to the length of x. So x is x1 through xn. And then you have this 1, which is for z0. And then the r1 is from z1 through zr. So, it turns out this z0 is important. So that's why I put the 1 here as opposed to r plus 1. So you give me a formula with so many variables, n plus 1 plus r variables. Then this souped up version of indiscernibility for this phi is the sentence I'm about to complete here. So first let's look at it formally, then I'll show you the picture. So the idea is that if you pick an indiscernible I, and if you pick two sequences J bar and K bar, increasing sequences in I. So this is what this formalism from Ramsey theory is using. So J bar and K bar are increasing sequences of length R from capital I. If you also are guaranteed that these sequences start after I, the I that we chose at the very beginning, then this indiscernibility condition holds. So this indiscernibility condition says that not only are in the old version of indiscernibility, J1 through JR and K1 through KR were present, and so were I, you could put I, but the new ingredient is X. You could also basically pick any inputs, any parameters of length n below I and stick them in the formula and be guaranteed that you have an equivalence. So it turns out that this scheme is also provable in PAI. And the proof of this is a little more work. I wouldn't call it a deep, but it certainly takes a little more effort playing with indiscernibles and the properties of PAI to establish it.
Ali,
I'm confused about something.
Yeah, sorry.
On the face of it, this would look like a like part of the definition of the indiscernibility. But here we are looking at this in your diagonal indiscernibility lemma.
Yeah.
I think you're looking at the scheme and you're looking at what really you can prove, which is not the same thing as what the indiscernibility means. I mean,
exactly.
This will be a completely immediate thing, but
exactly.
here it seems to
exactly.
have a price. What is it? Yes.
So one actually sees this this notion in set theory. It turns out, the indiscernibles one gets the so-called from O sharp. Indiscernibles in the constructible universe have this property. And
Sure.
And also this notion of indiscernibility came up in the proof of the Paris-Harrington result. In that case, it was only needed for delta zero formulas.
Okay.
Yeah.
Right, Ali. So, but there is also this connection to minimal types, and
oh yes, thank you. Yes, minimal types, exactly. Minimal types also. Yes.
They produce strong indiscernibles in this sense. But also, my question would be that, but in this proof, probably you need the full strength of PA star, right?
Yes, I do.
Okay. All right.
Yeah, at least the way I remember it. Yeah. Just to make sure that it's pretty clear what and this condition on indiscernibles is basically if you give me indiscernibles, the indiscernibles are in red. So you have I and J1 through JR and the same I and K1 through KR. Then you're allowed to, in just the pure indiscernibility condition is that I together with J1 through JR has the same properties as I together with K1 through KR. The diagonal part basically says you're allowed to use parameters below I. So that's
exactly. Yeah.
That's the added oomph in this case. Yeah. Okay. So this theorem is going to basically help us finish the other direction. There's a formula in the language of Peano arithmetic with this extra predicate for indiscernibles, such that in any model of PAI, this formula defines an inductive partial satisfaction class. So basically, the essence of the other direction. So to be able to give you a description of this formula, I'm first going to describe a recursive function that transforms each arithmetical formula into a delta zero formula with more variables. So the formula that you give me would have n variables. This is the phi of x here. And the formula I'm going to give back to you, which is phi star, would have the same variables as before, but also some new variables, z1 through zk. Whereas z1, the z's is a fresh supply of variables we add to the syntax of first order logic. The k that you see here, also when you look at the transformation, it will become clear that it's the depth of what I call the existential depth of phi. So if you look at the parsing tree for phi, you see along each branch what's the longest number of existential branchings that you see. So here we go. Also in what you're about to see, x and y range over the set of variables before we add this fresh stock of variables. To make things clean, I'm only assuming that logic is formulated using negation, disjunction, and existential quantification. And none of the fresh variables occurs in phi. So this star actually does almost nothing for a while, meaning for atomic formulas. Oh, sorry, this is the horror of me not changing from arithmetic to set theory. So this is supposed to be some atomic formula of arithmetic. So x plus y equals to z, for example, or some such thing. But basically, the transformation doesn't do anything except for the existential clause. For the existential clause, so you give me, there exists a y phi, and I'm going to transform it. I'm going to write down there is a y less than z1, and then I'm going to write down this funny formula phi star with the tilde on the top of it. Now, what is that? Well, phi star is just a transform of phi, the phi that was sitting here. So phi star is going to have variable z1 through zk. And then when I put the tilde over it, it just renumbers the variables, the z's, by replacing zi with zi plus 1. So it just shifts them over by 1. I'm going to give you another description of this transformation, which is going to be easier to see in one go. Another way of describing it is to first write, again, this is the curse of me not changing to arithmetic. So let this say phi of x is an arithmetical formula with n variables. This is what the symbol means. So if you give me an arithmetical formula with n variables, I'm going to find first a normal form for it. So the normal form is for all v1, there's a w1, ... and then the matrix here is a delta zero formula. And then I'm going to stick in those z's just where the outside quantifiers that you see are. So I'm going to write, instead of for all v1 less than z1, et cetera, et cetera. So this transformation definitely is the same kind of transformation that one sees also in the Paris-Harrington theorem. But here we're doing it for a different purpose. And in that transformation, one is using the Paris-Harrington theorem. Here we're using just the indiscernibility. And the key lemma is that if you give me a formula here, it's correctly saying L of PA as opposed to L of set theory. if you give me an n-ary formula of arithmetic, I look at the transform of it, which has now the same variables, but also z1 through, for some reason I've written z1 through zk minus 1. Then if you take a model of PAI and a tuple, a bar of length n from the model, and if you pick an increasing sequence of indiscernibles of length k in I, with the property that there is a buffer, there is a j such that the indiscernibles that we picked here start after j, and also your parameters are also after j. So if your j, your j is basically
parameters are below j.
yes,
Okay.
below j. Sorry, yes, the parameter
Okay, yeah.
below j. Sorry, I'm sorry. Yes.
True.
So j dominates the parameter, and the indiscernibles start after j. Yeah.
Okay.
Yeah.
Sure.
Then we have this very satisfying equivalence between the original formula and this transformed formula. So the proof of this lemma is basically using the apartness scheme. The diagonal indiscernibility can also come to say that it doesn't, this diagonal indiscernibility also assures you that it doesn't really matter which I1 through Ik you pick. This still will hold. But this is basically, this is the key lemma. So now with this lemma at hand, we are ready to define the satisfaction class. So imagine now that, remember, we have a model of m comma I, and within this model, we want to define a satisfaction class that is well behaved for all standard formulas. With one single formula, we want to define it. And this formula is allowed to use I. So the following definition takes place in m comma I. You bring me a formula of arithmetic with n free variables. I calculate its transform, and then I pick a j. I guess what I haven't written down here is that you bring me a formula, but you also bring me some parameters that I'm going to be sticking for the x's, just like these a bars. So if you bring me the formula, oh yeah, the tuple is right here. And you bring me also the n tuple, then I calculate the transform. I go to a j that is above the parameters, let's see. This seems to be a very nasty typo here. Sorry about that. So this basically, this tuple was of length n, and I just want all the elements of it to be below j. So this is what this j is confusing, because it looks like because j is also an indiscernible. So just ignore this part. So each ai from this tuple is below the j. And then you pick I1 through Ik to be the first k elements of I that are above j. So look, if I was not satisfying PA star, I couldn't do this. Within the model, I could not internally look for an element, the first element above the parameters, that was the j, and then after that, proceed to pick I1 through Ik. I could do it externally, outside the model, but I couldn't do it inside the model. So this is where PA star is used in a strong way. And then the satisfaction predicate is defined basically by saying, I'm going to deem phi members of S are precisely formulas phi of A such that their transform is deemed to be true by the canonical delta zero satisfaction class of arithmetic. Because it's well known that arithmetic is able to define satisfaction for delta zero formulas. It happens to be also sigma 1, but that's just not needed. We just need it to be definable. So this transformation here, this definition here, together with this lemma, shows that this particular S is well behaved. It picks the right sentences for all sentences that are standard, which would be now the end of the proof. So let me
If you
pause
want
now.
to do this in models of set theory, you need a little bit large cardinal strength or something. You know, I'm just wondering what, because you're essentially reducing the satisfiability to the delta zero by using the transform and having.
Yes.
Exactly. This has you mentioned it before. This has some flavor of like zero sharp or maybe anyway,
so it turns out this reasoning actually this lemma that I was just showing you works for also models of set theory. So verbatim, pretty much the same proof works. Actually, in the paper, the proof for set theory becomes a little easier even because set theory has limit ordinals and you're able to, but let me go back to I think the key thing you said was large cardinals. So it turns out large cardinals definitely will come and show their effect, but not in this lemma. But this lemma actually is useful. The fact that we can define truth is going to be useful to extract large cardinal strength from indiscernibles. But the actual lemma itself actually goes through quite nicely also for set theory.
Okay.
Yeah. Any other questions? Looking at my screen, unfortunately, I can't see the clock on my computer. Raman, could you remind me how much time I have left?
You have plenty of time. So at least 15 minutes. Okay. Or, this is an evening session, so take as much time as you want.
Thank you very much, but I will try to finish within time, and if I overspill, it will be just by a little. Because I just wanted to have about 15 minutes for the set theory part, but I think at this point, we're pretty close to that right now, because I want to draw some corollaries about this, the fact that expandability to PAI is equivalent to carrying an inductive partial satisfaction class. So the first corollary, or I guess the first part of the corollary would have different parts, is that there is no parametrically M-definable subset I of M such that M comma I satisfies PAI. Now, this is pretty actually expected, and it has an easy proof if I didn't put parametrically. If I just told you there's no M-definable subset, then which is indiscernible, you would say, of course, because if there was one, then I could distinguish the first element of it from the second element. So it turns out what makes it a little more work is the parametrically part. So you could prove this corollary either using the diagonal indiscernibility property and the argument I just gave for parameter free, or Tarski's undefinability of truth. If there was such an object I, then we could define truth within an inductive partial satisfaction class within M, and that's a no-no for, that's pretty much two proofs for part A, one using diagonal indiscernibility and one using the theorem, the main result that I just finished going over. Let's see, so I guess as you see, it says, therefore no other classes model of PA has an expansion to a model of PAI. What's B saying now? If M has an expansion to a model of PAI, then M is recursively saturated, and the converse holds if M is countable. Right, so this is definitely using the main result, and I don't see any way of showing it without the main result. So as soon as you expand to PAI, you must be recursively saturated, because it's well known that any model which carries an inductive satisfaction class has to be recursively saturated. This is one of the basic theorems of about recursive saturation. And what about this third part? This third part was, it comes up interestingly in the set theory part, but I first asked myself this question, in connection with the beautiful result of Jim from I guess it was in the 80s, maybe Jim can correct me. There's a result of Jim Schmerer that says if you begin with a model of PA that is recursively saturated, then you could find indiscernibles in the models that generate the model. Generate in the sense of using the notion of definability. Basically, every element in the model is definable from parameters in these indiscernibles. And I was wondering if something like that could be true for models of PAI. But it turns out, no, models of PAI, if you take a model of PAI and you look at the submodel of M, consisting of all the elements of capital M that are definable using parameters from capital I, that's what this M sub I is. Okay. Then M cannot be equal to M sub I. And this again is because of the fact that in PAI, you could define this partial inductive satisfaction. And if M were equal to M sub I, then you could pretty much map an initial segment of the universe into the universe, onto the universe. So it would contradict the pigeonhole principle, basically, if M was equal to M of I. Thanks to the main result. So M sub I is typically much smaller than M. And this last bit says that if you start with a countable recursively saturated model of a Peano arithmetic, it has an expansion that is prime, or in other words, pointwise definable, which satisfies PAI. So this part D is quite related to a beautiful theorem of Raman and Jim that says that exactly what you're seeing in part D, except that it says that you have an expansion to a inductive partial satisfaction class. And the proof of part D is pretty much looking at their proof and just at the right place using PAI and buying recursive saturation as opposed to inductive satisfaction classes. Meaning, I don't know of an easy way of proving this result. It's basically getting a piggyback right from the method of proof of the theorem that I just referred to, proved by Raman and Jim in the classic paper called Minimal Satisfaction Classes, I think. Am I right, Raman? Is that the name of the paper?
Yes.
Yes, very good. Okay. And then finally, lack of speed up. PIA has no significant speed up over PA in the following sense. There's a polynomial such that if you take any arithmetical formula and that formula has length L, and that formula has take an arithmetical formula which is provable in PAI, and the proof has length L, then we know there is a proof also in PA, and the question is, is there a polynomial transformation that does the job? And the answer is yes. So conservativity would be exactly what you're seeing in this implication without the red markings. If PAI proves phi, then PA proves phi. But if you also tell me the length of the proof, there's a single polynomial such that if you give me the length of the proof, then there's a proof controlled by that polynomial of the same sentences in PA. Right now, the only way I know how to prove this is to actually connect it to a result of Albert Visser, who showed that UTB has no significant speedup over PA, and basically transform this result to the UTB result and get home, thanks to the transformations that are available between PAI and UTB. In the paper, I pose a question actually whether this is true or not, and I actually figured this out only in the last week or so. That's why the question is still in the paper. The last question in the paper is exactly, does this happen or not?
Ali,
Okay.
do we know
yes.
do we know what this polynomial is?
Actually, it's probably quadratic and not worse.
I see.
This is kind of interesting in these kind of speed up results, or lack of speed up results. Typically, you either see linear or quadratic. I'm sure there are probably some exotic cases that are of higher order, but once I have a better, once I write it up, I'll be able to give you a better, more confident answer. Okay, now I just want to finish with just telling you just a little bit about how set theory story is both similar and different. Oh, it looks like I have a question. Let me pose the question. It's a quick question. I told you before that PAI is, from PAI you could transition to UTB and back. Remember UTB does have a standard model. So here I formulated UTB, so it's assuredly not able to have a standard model by adding a constant. So that's UTB super NS. So what I don't know is that even though PAI interprets UTB NS and UTB NS interprets PAI, it's not clear to me if they're bi-interpretable. And it looks like they may not be, but I don't know how to show that yet. Okay. Now, as far as set theory is concerned, you could pretty much anticipate what the axioms of this system I'm about to show you will be. The little twist here is that it would be really useful to have a global well ordering in your set theoretical setup, which Peano Arithmetic already has. Here I've introduced this extra relation symbol, which is going to globally well order the universe. And I have this axiom called GW for global well ordering. So the theory ZFI, just like PAI, is formulated not only by adding I to your language, but also adding this global well ordering. The models of ZFI with a less than as a subscript are of the form a model of set theory, global well ordering on that model of set theory, and a set of indiscernibles basically. But let's see what that looks like. So here I'm using ZF star in the same sense I was using PA star, except that here ZF star means you're allowed to use less than an I in the scheme of replacement, or in the scheme of collection and scheme of separation. So the natural extension of ZF in the language using less than an I. The idea being that you could set theoretically reason comfortably having the less than around and an I around. Also, as I said before, less than is the global well ordering. And it's a cofinal subset of the class of ordinals. So this is the theory now that is the set theoretical sibling of PAI. Oh, I guess I said it earlier, but officially I is a class of order indiscernibles over M comma I, M comma less than. So the indiscernibility is for the language of set theory augmented with less than. Any formula which is which has epsilon, its basic notions are epsilon and less than, with of course first order logic. I would be a class of indiscernibles for that. So in contrast with the conservativity of PAI over PA, this version of set theory is not conservative over ZF. So this is a big contrasting feature. And actually one can pinpoint precisely how much set theory does ZFI less than know. This is the main theorem of the paper actually is this theorem A. The following are equivalent for a sentence phi in the language of set theory. ZFI less than proves phi. So the system of set theory with the class of indiscernibles proves phi. If and only if an extension of ZFC proves phi, where this extension is obtained by adding a bunch of sentences. This scheme is basically lambda in honor of Asriel Levy. It consists of lambda sub n's for each natural number n. And lambda sub n is a sentence which basically says, not only there's an n malo cardinal, kappa, but that n malo cardinal has the property that if you cut off the universe at kappa, the model v kappa comma epsilon is a sigma n elementary submodel of the universe. So this can be said in one sentence. So n malo cardinals are generalizations of malo cardinals where 0 malo means that you're just strongly inaccessible, and 1 malo is the same thing as malo, which means that the class of strongly inaccessibles below you are stationary, i.e. they meet every closed unbounded set. And more generally, you're n plus 1 malo if the class of n malos below you are stationary below you. So these cardinals are well known to be way below, for example, weakly compact cardinals, and they form a hierarchy. And the third statement, which is equivalent to the first two, is that this fragment of, well, I shouldn't call it fragment of Kelly-Morse because Kelly-Morse doesn't prove order is weakly compact. This strengthening of Gödel-Bernays set theory with a statement saying that the ordinals as a class behave like a weakly compact cardinal proves phi. In case you're wondering what this means, this basically says that the analog of Koenig's lemma holds for the class of ordinals. If you have a tree on the class of ordinals that is set branching and is unbounded in the class of ordinals, then there's a branch. And also, of course, there are other versions of weak compactness. You could also say that ORD arrows ORD 2-2 in the Erdős notation. Or a particular logic has the weak compactness property. The equivalence of 2 and 3 was proved in an earlier paper of mine. And the equivalence comes really handy in establishing this theorem because it turns out to go from 1 to 2 and from 2 to 3, well, of course, from 2 to 3 is just what the result in my 2004 paper. From 1 to 2, you could use this old result and pretty much get the job done by a pretty straightforward reasoning. But the harder direction for me was to show 3 implies 1. That if GBC plus order is weakly compact proves phi, where phi is just an ordinary set theoretical statement, then this system of set theory proves phi. And for that, I had to prove a theorem which I'm going to put this. It's a lemma, actually. I'm going to put this lemma because I want to show you how it's true also in the arithmetical world, and you can kind of see what's the key difference between set theory and arithmetic by looking at the lemma. So before I state the lemma, I'm going to use the notation M sub I for the elementary submodel generated by the indiscernibles. Let's see. Looks like here I haven't written down that it's the elementary submodel of M generated by M definable functions from I, meaning it's what I generates in M sub I. So I is missing in this sentence. And M sub I plus J is the elementary extension of M sub I resulting from stretching I to the linear order I plus J. So to repeat, M sub I is just the set of objects in the model M that are definable using parameters from capital I. And Mi plus J is the result of stretching this model M sub I, stretching in the sense of model theory, stretching indiscernibles, where you go from I to I plus J, where the idea of I plus J is basically members of I come before members of J. So if you begin with a model of this theory, ZFI sub less than, ZF with the class of indiscernibles. And if you pick a linear order that doesn't have a minimum element that is disjoint from your model, then if you let this fancy X to be the coded subsets of the first model in the sense of the second model, I'll show you a picture in a second which would make this a little more clear, then the following hold. So before I show you what the following holds here, typically one sees this notation in arithmetic or set theory if M sub I plus J is an end extension of M sub I. And the first statement of the theorem, of the lemma rather, says that when you stretch the indiscernibles in a model of this theory, you get an end extension. Moreover, J is downward cofinaline in the new part of Mi plus J without Mi. And by appending this fancy X to M sub I, you get a model of GBC plus orders weakly compact. Basically, if you look at this lemma and wonder to get a feel for it, like what happens in arithmetic with the same setup, you get an end extension of M sub I such that M sub I is a strong cut in Mi plus J. Now, strong cuts in models of arithmetic basically means that the cut is a model of arithmetic. For set theory, a strong cut buys you lots of n-model cardinals and more generally GBC plus orders weakly compact. So let me show you a picture maybe. Oops, too fast. So this is the picture. You begin with a model. The black model, black ink model is the model which carries these indiscernibles, the green indiscernibles I. Then you look at the model that they generate, meaning the indiscernibles generate the model M sub I. You stretch that to the model M sub I plus J by, remember J has no first element. And then this stretching results in an end extension. You then grab this fancy X. Intuitively, this fancy X is the result of intersecting definable subsets of this big model with M sub I. This is what these coded subsets are about. It's like the standard system in arithmetic. And that results basically in a model of GBC plus orders weakly compact. So to finish the story of comparison and contrast, and at the same time thanking you for your patience, I'm going to be showing you a picture in a moment, but let me draw you some corollaries. So this corollaries actually is where shows you somehow something that one couldn't notice in arithmetic is happening here. First of all, because of the fact that this theory is able to talk about, require at most n-model cardinals, it is consistent with V equals to L, assuming a modest large cardinal hypothesis. Here, the modest large cardinal hypothesis is, for example, an omega model cardinal. On the other hand, if you have an omega model of this theory, an omega model means a model whose set of natural numbers is externally viewed well-founded. So it doesn't have any non-standard natural numbers. If you have an omega model of this theory, then O sharp exists. And much stronger forms of V is not equal to L, such as there's a proper class of almost Ramsey cardinals exist in the core model. So there's this big branching basically in this set theoretical story between the omega models and the non-omega models. The non-omega models allow V equals to L. The universe is constructible, but the non-omega models don't. It's in the proof of theorem B actually that the truth definition that I was just showing you earlier for arithmetic also works for set theory, and it buys you basically an elementary embedding of L into itself. So this is pretty much the very, very brief outline of the fact that if you're in an omega model, the truth definition allows you to define a non-trivial embedding of the constructible universe of the ambient model into itself, and that's well known to imply O sharp. In particular, no well-founded model of ZF that satisfies any of the conditions below has an expansion to a model of ZFI. If the model satisfies V equals to L, or if the model is V kappa for some small large cardinal, such as inaccessible, malo, weakly compact, ineffable. I like to think of this corollary B as basically the continuation of a story which began with the observation that the standard model of arithmetic does not expand to PAI. Remember, the proof of that was very simple. Basically, the standard model of arithmetic is pointwise definable, so it's not expandable to a model of PAI. So it turns out, actually, for a long time, many V kappas have the same property. They don't expand to the set theoretic analog of PAI. But by the time you get to a Ramsey cardinal, they do have such expansions. So that's perhaps an intuitive way of looking at it, of how being an omega model basically is, being the standard model of arithmetic falls under category A in a way, because V equals to L holds in such models. So I'll just close with this slide just to give you an idea what happened in this talk. If you look at the top part of this equation, you see theories that are intimately connected. Let's look at the bottom part actually first. PAI and PA and ACA0 are connected in the sense that PAI is a conservative extension of PA, and ACA0 is also a conservative extension of PA. In the set theoretic realm, ZFI with less than is a conservative extension of ZFC plus lambda, and this class theory is a conservative extension of ZFC plus lambda. Thank you for your patience.
Thank you, Ali. So now it's time for questions.
I have one question, perhaps. Thank you very much, Ali. The first question is a kind of at some point you mentioned a contrast between the result by Roman and Jim Schmerl on the prime models. I think you said prime models and the road.
Yes, yes.
Slightly different. And the fact that for this theory, prime models are, I mean, you cannot really catch them in this. So somehow there is some structural difference between the models of the two theories that is, I think, interesting. Can you say a little bit more about these two, this contrast?
I'm sorry, as far as the contrast, were you referring to?
Yeah, that there was this theorem that every model could be obtained as the final or prime of
yes,
some
yes.
In the case of PA, but not for PAI.
Yes, and, actually, the proof, okay. Actually, that theorem also holds for set theory, in the sense that if you have a recursively saturated model of set theory, that is also additionally a model of lambda. So coming back to this theorem, even though PAI doesn't give you any new arithmetical theorems, ZFI gives you new set theoretical theorems, and they're precisely what you get by adding this scheme that I call lambda. So the analog of the theorem that I just mentioned was that if you begin with a recursively saturated countable model of ZFC plus lambda, then there is an expansion of that model such that it satisfies ZFCI, and additionally, every element is pointwise definable.
Okay.
Yeah, and that's basically. I mean, going back to the proof that that is for arithmetic. Usually, these results are stated for models of PA, but practically all of them go through also for models of stronger theories such as ZF, as long as you're looking at, let's say, countable recursively saturated models. So, so if the model is not recursively saturated, of course, then, like in this case, we saw that the omega models of set theory with indiscernibles behave very differently from the non-omega models.
Yeah.
So in that regard, the two theories behave alike. The other way that they differ, I should say, is that in ZFI with less than, you could define a truth predicate on the ambient model of set theory that is full, in the sense that it decides every formula according to Tarski rules. But in PAI, we at best can do that for standard formulas. So this is actually an interesting contrast between them. The truth predicate that you get, or the satisfaction predicate that you get in the ZFI system, is much better behaved than in the arithmetical case, which is, it's always interesting comparing and contrasting these two theories, because in many ways they behave alike, and in many ways they also are quite contrasting. And by just looking at a particular result, it's not quite clear yet, and there's no magic test which tells you which way to go. And of course, it's these contrasting parts that are more interesting than the similarities. When the proofs, when the same theorem holds for both, it's usually the same proof more or less.
But when there is this branching, yeah. But in a way, there was something, you have to strengthen ZFC with some, with your n model cardinals or something to get a behavior that starts being more similar to Peano arithmetic, which is at least in this respect.
Yes. I mean, for me, it's a philosophical. I mean, of course, there are many ways of motivating large cardinals. This is one motivation, one way of basically motivating this kind of large cardinals, because these cardinals not only are have a model property, but they also have a reflective property that if you cut the universe at a particular place, there, the lambda n's basically say that the kappa is n malo and n reflective, so to speak. So in a way, for set theory to mimic the behavior of arithmetic, it has to be endowed with large cardinals. Is the kind of the summary of this picture we're looking at. Yeah.
Ali and Andres, perhaps this might be a silly question, but looking back from theory to arithmetic, perhaps the import is then the fact that you have to add this lambda, you have some large cardinal assumption, is that in PA you have strong cuts. And that's what somehow, there was some remnants of it in the proofs here, that indiscernibles somehow know the. But so is it so that in ZFC without larger cardinal axioms, well, there is no such thing as say, strong cuts, that you need some combinatorial strength for initial segments?
Yes, absolutely. What you said is correct. Basically strong cuts are non-existent a strong cut, basically, as soon as you have a strong cut in the model of set theory, the cut has to satisfy lambda. And that's the huge contrast with arithmetic, yeah. And of course, somebody who thinks that lambda is obviously true would say, you should have added it to begin with, It's interesting that usually the discussion of large cardinals for some time has focused on motivating much larger cardinals, that are up in the hierarchy of large cardinals. But somehow this project is able to motivate these kind of baby large cardinals by just looking at the behavior of arithmetic. And it will be interesting to see if there are other large cardinals that one can motivate this way. There's a way of, I would just say something quick. There's a way of strengthening ZFI by basically adding a scheme which says that I is not only unbounded in the class of ordinals, but also definably stationary, meaning it meets every definable closed unbounded set. And then it turns out that corresponds to a theory ZFC plus, let's say, lambda plus, where instead of n malo, you have a notion of n ineffable cardinal, which is definitely one head and shoulder above the n malo. So. But there are the ones I know of are always in the realm that is below the
Zero sharp.
yeah, exactly, zero sharp. Yeah, they're within the V equals to L realm. Yeah.
Yeah, so Ali, this is exactly the question that I was going to ask you. What are the possible strengthenings that give you other large cardinals? So is there anything other than an ineffable in the stationarity example?
No, not basically. The most I can say is exactly this adding stationarity. Unless there are other properties one can think of that are formulatable in first order logic about the predicate I, but I couldn't think of any.
Because I was also wondering about this. So the second order part, the GBC plus orders weakly compact, whether there was some on OR that you can make and connect them also in some way. Right.
So if we add, if we bump up ZFI by insisting that I is definably stationary, then ORD would be, as I recall, n ineffable for each concrete natural number n.
Okay, I see.
That would be. Yeah.
I see. That's very interesting. Okay, is this in your paper, Ali?
What I just told you is in what I call the parting shot of the paper. It's in the last remark, which in the next draft it will be more elaborated. Because it's basically the tools are the tools that are needed for the ZFI plus some standard machinery connecting ineffables with the Ramsey property, meaning there are different formulations of ineffables, and the formulation in terms of I think it was given by Baumgartner is the one that is the best way of seeing that by adding to GBC that ORD is n ineffable for each concrete number n, you can prove that the class of stationary, the indiscernibles are definably stationary and vice versa. So in other words, I think somebody who knows the Baumgartner theorem, not the proof, the Baumgartner theorem and the methods of the paper can pretty easily see how to modify them to get the claim that I just made.
Okay, I see. Yeah, this is super interesting. And by the way, thank you for this great talk. It was so interesting.
Yeah, pleasure as always.
Can I ask a last short question, Roman? Or should I
it doesn't have to be fast, but go ahead.
Okay. Sorry. Yeah. It's just in recent years there has been all this talk about reflection properties and large cardinals, but of course that's at the very high end of the spectrum compared to these ones here. But somehow the long story of the reflection property, and I'm sure that in other seminars, but like in Vika's seminar and so on, this has been discussed at length, refining like the CN reflecting cardinals by Bagaria and collaborators, and there is some kind of parallel flavor, but the main difference is there is no arithmetic, or somehow the parallels with models of arithmetic somehow completely break, and they actually find parallels with models coming from somewhere else, from algebraic topology these days. So Bagaria and his algebraic topology collaborators have started, they started from Vopenka, and then they started going down, and then Magidor came into the picture as well, and they started kind of not really translating, but interpreting, perhaps is a better word, phenomena that are important in algebraic topology, that somehow happen in a natural way in algebraic topology, just as some of these phenomena that we saw now happen in a natural way in models of Peano arithmetic, like the gaps that Roman was describing.
Yes.
And they start refining and finding, the CN cardinals, all of these. It's just, it's like the jump from small, large cardinals to large cardinals seems to correspond to interpreting modes of arithmetic versus interpreting modes of maybe some kind of algebraic topology that we don't quite know. I don't have much more to say, but I just observe that there is this refinement that is also happening up there.
Interesting. I was aware of the connection with, I thought, category theory, meaning the work that Bagaria was doing and Poppenka's principles and whatnot, but I wasn't up on the fact that actually there are these algebraic topology connection as well, as opposed to somehow I was under the impression that it's just abstract category theory.
I think the link, the original link, was so-called accessible categories. So somehow accessible categories turned out to be in the neighborhood of, I think, originally Poppenka, and then they refined it on the large cardinal side. But these are very natural in algebraic topology. So he started working with, I think Casacuberta is the name of his algebraic topology main collaborator in Catalonia. And they started really, kind of refining and threading, more phenomena coming from algebraic topology and finding all these, CN cardinals and so on. Maybe somebody else here knows these cardinals. Vika, I'm sure, or some other people would have seen these cardinals. This is all I can say. In the details, of course, it's extremely different details, but these, hierarchies and the interpretations and reflection properties, because you also have some kind of reflection properties going on here linked to indiscernibility, very, very specific kind of reflection properties.
Actually, I have to go back and look at that paper of Bagaria you're mentioning, because I'm now curious what distinguishes CN cardinals from N reflecting. What more do you need to add to be a CN cardinal? I don't know, Vika or anybody else remembers?
So Andres, are you talking about the CN extendables? Because that's an extension of extendability. So it's just you take an extendability embedding and you require an extra property of it. So they're way up in
yeah. Oh, I see. Okay.
Like up to sigma, and yeah, they're way up. They're really, in the neighborhood of super compact, or maybe it's really quite, or no. I think there are two versions, Vika. There is the extendable one, which is much, more way up. And there is one version that is kind of below super compact, and it's also CN something. And the CN just refers to sigma and kind of a reflection property that is encapsulated in the definition of those cardinals. But those are second order reflection properties, not first order, like here. So it is, but maybe some something in between could be interesting, looking at logics that somehow go between first order and second order and try to see what happens. Even going up from modes of arithmetic, I don't know. Or maybe
this discussion is just remind me of something that I just remembered about the fact that Jeff Paris did his dissertation on basically measurable cardinals, and then he transitioned to arithmetic. And I remember hearing that he carried a lot of the intuitions about large cardinals to the way of understanding the behavior of cuts in models of PA. And I know Laura Kirby also has done some beautiful work in that direction. The flipping properties, for example, of cuts, comparing them with the flipping properties in large cardinal theory. But the story you're describing about these larger cardinals, I haven't seen appear, but then again, it could very well be because of the fact that this is hasn't been a tremendously active area, as you can imagine. And the intersection of large cardinal theorists and models of arithmetical enthusiasts, as set of measure 0.
I see Cameron has a question.
Yeah, I had a small question about your analogy on the screen.
Uh-huh.
So I know how to go from a model of PA. Maybe you already said this, and I'm asking you to repeat something, in which case I apologize. But I know how to go from a model of PA to ACA naught. You just put on the definable sets.
Yes.
But to go from a model of ZFC plus your lambda to Grotto-Bernays plus orders weakly compact, like you have a paper, I think with Hampkins, that this gives you undefinable classes. So it's not just putting the definable classes on. So do you have like a procedure that like, you know, you explicitly say what the classes you put are on to give you a model of this orders weakly compact from this ZFC plus lambda?
That's a question that I didn't know the answer to, meaning I only knew before I wrote this paper that there is such an expansion, but I didn't know of an easy way of describing such an expansion. And then in this paper, I describe a theory which is basically same as ZFI, except that you have more than one class of indiscernibles. You have like the first class of indiscernibles, which are indiscernible over the ambient structure V comma epsilon. And then you have another class of indiscernibles, let's say I2, which are indiscernible over V, meaning the universe comma epsilon comma less than, and then comma I. So indiscernible with respect to adding I basically to the structure. And you then iterate that, and you get a theory with omega many indiscernibles, each getting in a way stronger and stronger over the, and each is indiscernible over the previous part of the universe. If you take that theory, it happens to be still giving you ZFC plus lambda as its basically set theoretical consequences. And in that theory, if you look at the definable subsets, you'll get GBC plus orders weakly compact.
So you mean definable with like these extra parameters?
Exactly.
Okay.
Yes. Yes.
All right.
So,
thank you.
Yeah.
Any more questions?
I wanted to ask about the proof of one of the corollaries earlier on of in the PA case, that if you can expand to PAI, then it must be recursively saturated. And I think you mentioned that you went through this sort of intermediate where essentially it's sort of you expand to PAI, therefore there's a satisfaction class, therefore it's recursively saturated. Is that
Yes, yes, that's exactly right. Yes.
Yeah. I think that there should be a sort of more direct proof using this translation thing that you have, right? Like your phi to phi star translations. You sort of you take like a recursive type and then P of X, and then you could probably form P star in some way, and then you've gotten a type of bounded complexity. And then you can use the fact that bounded complexity types are satisfied, et cetera. And so it's sort of maybe there's a more direct way to see that.
No, I think what you're saying sounds right to me. So just to directly use the transformation to use the fact that, because we know that types whose members are of bounded complexity are always realized, and yeah, I think your outline sounds right on the nose.
Right. Yeah. Because it seems like there's a sort of a very, very sort of direct connection there. I was thinking initially it might have something to do with sort of types that you can sort of minimal types in those models, but that might be that didn't get me anywhere when I tried to sketch it out.
Right. No, it's interesting. Yeah, these minimal types, and usually these because both in arithmetic and set theory, one knows of a lot of models where the indiscernibles are co-final in the model, and typically when you append them to the model, they don't satisfy PA star anymore. So that because the same thing happens in set theory. If you append the indiscernibles from O sharp to L, then you won't be getting a model of this ZFI, so to speak. But it would be interesting to see how somehow different ways of getting models of PAI other than the ones that I just described using maybe minimal types in some other clever way.
Right, so what just Atar said that in a model with an inductive satisfaction class, partial satisfaction class, you can get those inductive I's by using minimal types as well, because then you just show that there is a definable cofinal subset of elements realizing a given minimal type that's definable from that class, some non-standard parameter.
Did I hear correctly that these indiscernibles would be then satisfying PA star when you append them?
That's right, because they are defined. You define them in MS. You have a satisfaction class S.
Oh, in MS. Oh, I'm sorry. Yes. Okay.
But this is a long way of getting a set of indiscernible like that, but really from both inductive satisfaction class and a minimal type realized in a model.
Yeah. I just remember this discussion reminds me of, I don't know if, in PAI, we have this truth definition that I gave, and that truth definition we know typically only works for standard formulas. But we can add an axiom saying that this truth definition works for all formulas, an axiom in the language of PAI. Right. I don't know what happens to that theory, and it might be a natural strengthening of PAI. And in particular, PAI doesn't prove Paris-Harrington for the same reason that PA doesn't prove Paris-Harrington, but I have a nagging feeling that there is a natural way of augmenting PAI with some axiom which gives it more arithmetical power.
Mm-hmm. I see.
So,
well, that's an interesting question, though. To look for some PAJ when with J of certain properties that carries arithmetic power.
Yeah. And so I'm not even sure if the theory I just described, for example, let me describe the theory again. So we have this canonical definition of an inductive satisfaction class within PAI. And so let's call that definition given by sigma. And we write an axiom saying that sigma is full. It decides, sigma basically is a full satisfaction class. It satisfies Tarski's axioms for all formulas. And it's not clear to me if this is consistent, and if it's consistent, if it's more powerful than PAI. So that's like a natural candidate.
There is something in Laurie's thesis about, I don't remember whether there were super strong cats. Now, when in strong cats, you have Ramsey theorem, infinite Ramsey theorem with coded subsets for any standard exponent. But I think super strong cats, you have Ramsey for a non-standard exponent. And I don't remember now. It's something interesting that's happening there. There might be some link between those two.
Yes.
I don't remember exactly either, but it did imply recursive saturation. When you have
well, so it's all in one bag, right? Yeah.
Interesting. Yeah, because in ACA 0, you cannot prove Ramsey's theorem if you quantify over the exponents. So that's that would be a natural strengthening of ACA. So for each concrete version of Ramsey's theorem for a fixed exponent, ACA 0, of course, can prove it. But if you quantify over the exponents, then that statement is not provable, is known to be not provable in ACA 0. And maybe these cuts that you're describing that Laurie has worked on correspond to that strengthening of ACA 0.
Well, maybe it's time to look at those cuts because, Laurie, if I remember well, it's in your thesis, but it's in none of the papers that you later published. There was nothing much that was done.
That's correct. I never published it. Yeah. And it was never really tidied up, as far as I remember.
Time to do it.
Yeah, I noticed Joseph Quincy, who wrote his dissertation in 1980, last year LaTeXed his dissertation and put it on archive. So maybe Laura could do that to his dissertation, because I would love to have a copy, but the last I asked Raman, I think it's in his office.
It's sitting somewhere
somewhere
on the 4th floor at the Graduate Center.
I think it's in my mom's house.
Oh,
She lent it to me while I was a grad student there, and I have it. I had it there while I was working on my thesis, and then well, I haven't. At some point after the pandemic, I have to visit her and grab it.
Well, I think I have one, so I could maybe send it to you.
Oh, you have a PDF copy?
No, not a PDF. No.
No, but it would be nice to have it digitized. All the theses that Lesham's thesis got published, and Wood's thesis got published, and I think your thesis, Laurie, also should be published somewhere. Because there is
just rather somebody else did the LaTeX.
No, but maybe there is some software that we just read the print. We'll see. No, somebody would have to type it. That's true.
Yes, but even a PDF which can be then rendered, searchable would be great. Yeah.
Okay, then. So I guess that would be it for tonight, as far as MOPA is concerned. Next week we're going back to 2 p.m. So with apologies to our friends at the other end of the globe. And Damir will talk, and it's an interesting title. So
what is the title?
I already forgot. I looked at it a moment ago. It is reduction games, provability, and compactness, but it all has to do with reverse math.
Very good. Thanks again.